Hello gamers, welcome to another video. So many database implementations will have the option to save the contents of the database to a file, which will then be read when the database process restarts in order to repopulate the database. This will allow for the data to persist when the actual database process stops. The purpose of this project is to look at several different database implementations and see what fun things we can do if we control that file, as well as just general understanding of a lot of the functionalities within a database. Today, we'll be looking at the Tokyo Cabinet database implementation. So, a bit about the Tokyo Cabinet databasing software. You interface with it through a C API. It has different database types or styles. The type we will be looking at for this project is the hash map based one. The version I worked against is 1.4.48, which at this time I believe is the latest database version. However, I think development on this project may have ceased as of now, and there's a link to the project if you want to take a look at it. So next up, I want to briefly cover how to actually use this database implementation. Like I said previously, it is interfaced with via a C API. So I will now cover two C files that are which are based off of the examples provided with the project that actually use the API. First one is database file creation.c. Purpose of this file is to create a new database and then insert records into it. It will start off via creating a new database object, then opening up a database. It will then insert records, which in this case are just key value pairs right here, here, and here. Then it will close the database and then delete the database object. The second file that I wrote, purpose of this file is to simply query that database for a record where the key is that right there. It will start off via creating a new database object and then open up a database and then retrieve all records associated, or retrieve a record associated with this key, print the value, close the database, and then delete the database object. Now, to actually compile it, let me just go through my bash history right here. Okay, we can see right here are the two binaries which were generated from our files. First, we run database file creation. We can see it actually generated a new database save file right there. And then when we run database querying, we see that will actually give us the value that corresponds to the key that we queried. And that's how you use the Tokyo Cabinet C API briefly. So next up, I want to briefly discuss hashing. This is because the particular database type within this database implementation that we are using primarily relies on hashing a key in order to actually locate where the record should be. From our perspective, this primarily happens in this function right here, tchdb_bidx. Now, interesting thing about this function, it will actually generate two separate hashes, the first being the return value and the second being written to this pointer that is passed in as an argument. Now, why is this? The first hash that is generated, the primary hash, is used as an index into the bucket array, and the second hash, now hash collisions occur within this database implementation with the hashing algorithms used. In order to remediate that, the primary hash doesn't index to a record and indexes to a bucket which can contain multiple records, and the secondary hash will be used to uniquely identify a record within a bucket. Now, one thing I did do over here is a Python 3 script that will emulate the behavior of the hashing algorithm and allow us to see the primary and secondary hash of a particular key. I'm not going to, in this video, go in depth step by step as to how this hashing algorithm works, but it's there if you want to see it, and it's also in the docs linked in the description. We can go ahead and run this, and we see that for this key right here, it generates this primary and secondary hash, with the primary being used as an index into the bucket array and the second being used to uniquely identify this record, within the bucket when hash collisions exist. So next up, I want to cover the actual structure of a database save file. For this, I'll be using the same database save file created in the previous step from the database file creation.c. So let's go ahead and pop it open in a hex editor. Now for this database save file, there are three main parts to it. The first is the database header, the second is the bucket array, and the third is the section that actually stores the records in the buckets. We will start off with the header. Now I'm just going to take a quick look at my docs over here. The header consists of certain values at specific offsets within the headers that mean certain things. For many or several of these header values, such as the database type and additional flags, I'm not 100% sure what those values actually mean, like a value of 0 means this or something like that. But let's start going through some of these. It will start off with a string that will signify the database name and the version. In this case, it's Tokyo Cabinet 1.0.91. Preceding that, an offset OX20 is a single byte value meaning the database type. Here is a single byte value that means the database, well, the flags associated with the database. I'm not 100% sure what this means. Right here, we see is a single byte value meaning OX04. This is for the power of record alignment, which what this means is 4 bits. This value is going to come in handy for a moment because it's what the offsets from the bucket array are shifted by. Here is the power of the free block pool number. I don't know what this is or what this means. After here is a 4 byte value. This right here, options, not 100% sure what that means. Right here is a 4 byte value, which is the number of buckets in the bucket array. I believe I got this value, I think, through either pausing in a debugger to see what it is or just manually reversing out the, the database implementation. I'm not sure which, but I know one thing from here. Let me pull it up. TokyoCabinet.hash. Yeah, bucket number. It actually came up in some previous parts. So moving on, we have the number of records at OX30, which is OX03, which that makes sense because that database file create only inserted 3 records. After that, we have some other values such as the size of the database value at OX38, which we see is about OX081180, which coincidentally, if we go to the end of this, OX0811.9F, yeah, that is actually the size of this file. And then what else? At offset OX40 is the offset to the first record, which is OX081140. By the way, many of these values are at least Indian. Now, moving on, the next section that we have is the bucket array section. This section is the largest one in the database file. It covers the majority of this file. Basically everything that starts from here all the way down to about here, give or take. And what this section actually will hold, well, remember back to the hashing section, the primary hash is used as an index into the bucket array. And within the bucket array, it will have an offset. The bucket array itself does not actually store the buckets, it merely stores the offset to the bucket. So over here, we have this Tokyo hash offset.py file. This script will actually, we can give it a key and it will generate the offset within this file to that. How does it do it? Well, it uses the same logic as the primary hash calculation done in this, in the original Python script. It just takes that number and multiplies it by 4 since that's the size of the integer, and adds OX100 to it since that is the offset to the start of the bucket array, and it will just output that offset. You can check out the docs for more details as to why that is, but we can go ahead and run it. And we see that based upon the keys, we get three separate offsets: OX11410, offset OX7318C, and offset OX3E380. And when we go to those different offsets, go to byte OX11410, we see is the value OX8114 stored in least Indian. Now, one thing, remember back to this value I was talking about. Let me scroll all the way back up here. This OX04, this represents the number of bits that offsets in the bucket array are shifted over to the left to. So, oh wait, not find. Let me, where's go to? So this value right here, OX8114, it's really offset OX81140. So the offset to the bucket array which stores the first record is OX81140. And let's find the other two, OX7318C, offset OX81160, and finally OX81180. So the record or the buckets are stored at offset OX81140, offset OX81160, and offset OX81180. And when we go down to it, you see right here, start of the first bucket is right here. Now, to cover the final section of it, which is actually the buckets and the records where they're stored, I'm going to cover that now. First off, what is a bucket? A bucket is just a tree of records. Records are individual nodes within the tree. So I'm going to briefly cover the format of it right now. Let me scroll down. Bucket records. Okay, cool. So this is briefly the structure of a bucket or a record. I'm going to go over them now. First off is a 1-byte magic value. It's always going to be OXC8 from what I understand. The second is the secondary hash value. So when we go ahead and generate the secondary hash value, we see that for the first record, it's a single byte value OXAE, which you see that it's stored right here. The secondary hash value is used when it's searching through a bucket in order to deal with hash collisions. Following that is a 4-byte integer. So a record is a node within a tree. It has a left child and a right child. The first value, or right here, is a 4-byte integer, meaning the offset to the left child, and this 4-byte value right here is an offset to the right child. Now, when it's searching through a bucket, it will compare the secondary hash of the key it's given to the secondary hash right here. And depending on what the comparison is, it will search either through the left subtree of the current record or the right subtree of the current record. In this instance, this database is fairly small and doesn't actually have any hash collisions, so there are no children of this. Now, moving on is a 2-byte integer right here. In this case, it's just OX03. This is the size of the padding at the end of the record. Followed by that are 2 single byte values, which are the length of the key and the length of the value. And then we have the actual key itself, which is 5 bytes long. 1, 2, 3, 4, 5. And then we actually have the, the value of the record. In this case, it's 10 bytes long. So you can just go through it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have the 3 bytes of padding, 1, 2, 3, which brings us to the start of the next record, which is OX81160, which from what you saw from our previous work in the bucket array is the start of another bucket. So going through here, we see starts off with the magic value OXCA, and then the secondary hash value of OXA7, which does match what we expect it to be. Following that are 8 null bytes because there are no children of this record. Following that, actually, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are actually 10 null bytes. Reason for that being is these 2 bytes right here that represent the sides of the padding are 0, so there is no padding at the end of this record. We just see that the size of the key is 6, and the size of the value is, I believe, 12. Yeah, that should be 12 if I did the math or hex to base 10 conversion right in my head. So we have this 6-byte key, and then we have the 12-byte value. And then right after that, we have offset 0x81180, which is the start of the final record, which is quickly going through its secondary hash value 0x8d, which is what expected to be. Let's see. 8 bytes of null bytes. And then we have 1 byte of padding, 6 bytes of key, 11 bytes of value. We have the key and the value pair right there. And then we have a single non-byte of padding, and that is the end of the database save file. And just like that, I've covered roughly or briefly the structure of a database save file for Tokyo Cabinet. So next up, I just want to briefly go over the actual code for how record lookup or record selection happens. We see here, this is database querying.c. It starts off with the tchdb get2 function. So when you go through the source code and look at it, this is the function right here. We see that it effectively just wraps tchdb get, which that function is right here. Looking through here, we see I'll call tchdb idx. This will generate the primary and the secondary hashes for the given key, which it will then call this function right here, which it will actually handle a lot of the logic for actual record selection. So when you go there, let's find it here. Wait, yeah, here's the function right here. So one thing I was talking about in the previous section with the hash and how, depending on the comparison, it will either go to the left or the right subtree of the record. That logic actually happens right here. Taking a step back, this is a while loop. The purpose of this while loop is to actually iterate through the bucket, searching for the individual record. We see here that if the hash is greater than the current record hash, I believe. Let's see. Yeah. Okay. Taking a step back, this tchdb readrec will read the current record that it is iterating through for the record. Compare it here. If it's greater than, it will go to the left. If it's less than, it will go to the right subtree. After that, it will attempt to check if the key in the record matches the given key with this function call right here. And then assuming that the key, well, this right here are some checks to verify that that comparison actually did work. Assuming that did work, it will call this function call right here to actually read the contents of the record. Preceding that is some other code that I believe is not for the common case, but I'm not going to cover that right now because this is meant just to briefly cover it. So next up, I want to briefly discuss the code path taken for inserting new records. This right here is done with the function tchdb put2, which we see will insert a new key value pair as a record. This is from the file database file creation.c. There are other function calls we can call from the API that will insert a new record, but I did it with this function. So looking for this function right here, we see it's right here. It basically will just wrap this function right here, which we see is right here. Also, this code path is going to be similar to the selection code path. We see similar to that code path, it will call this function right here to generate the primary and secondary hashes, and then call this function right here in order to actually handle the logic of inserting the record, or rather finding where the record should be inserted. So there are two cases that I'd like to briefly discuss with this. The first case is when the record does actually exist in the database, so effectively we're just inserting over an existing record or otherwise updating a record. In order to do this, it will need to first find the record, and this is done with a while loop that looks pretty similar to the while loop from the selection code path. You see that will perform similar comparisons against a secondary hash and then the key. And then assuming all of that passes, we'll see that we'll call this function right here in order to actually update the record. This right here is code dealing with what I believe is special cases for you have the database in a particular mode. But assuming that it is a new record, that means that this record doesn't exist in the bucket. That means that this while loop will iterate through it without actually finding the record, which this code right here will handle the process of actually inserting a new record, which is done right here. So now that we actually understand a bit about how this database implementation works, assuming we can write to the database save file, what fun things can we do? One thing that I found that we can do is we can leak data. What I mean by that is when we query one record, the data returned not only is the value of that record, but we leak subsequent data in the memory. And I'll now be showcasing that. For this, there are two files, database file creation and database querying. Database querying is a little bit different than the one I have been using so far, but I'm just going to show those two files right now. Database file creation is more or less the same though. But looking at database querying, primary difference here is the database it loads is leak-fighter-z. Reason for that being is I have database file creation, which will create the file, then I'll copy it over and then edit it just for, well, make the demo a little bit smoother. But let's go ahead. I'm going to run database file creation in order to generate the database save file, and then I'm going to copy it over to the file that I wish to leak. There we go. First off, I'm just going to run database querying just so we can show the query under normal situations, and we see that it just returns the value that it's supposed to be. Now I'm going to open this up. Also, for context, I am just basically going through the same demo I have in the docs I linked in the description for this. But let's go ahead and look through this. For this, let's scroll all the way down. So the record that we're currently querying is this one right here. And what I want to do is I want to go ahead and leak the subsequent data. First off, what I'm going to show you is for this database querying, I'm going to throw this in GDB, if I can type this correctly. And actually, let me go for the code. So how I'm going to show you the actual data. Right now, I am displaying the data through a printf statement with %s. And one issue with that is for this, if I'm leaking subsequent data, I might actually get data. I might actually get like an OX 20 or 30 size block, which will contain all of this. However, this null byte right here will cause the printf to start printing out the bytes. So what I'm just going to do is break on this printf to see what the data returned is. That's why I'm throwing this in GDB. Break at print. Wait a second. I think I have to break at main first. That did not work. Printf check. I'm just going to break at main plus 52. That should return a pointer to, yeah, the return value is a pointer to the value, so I'm just going to break at main plus 52. And the return value is an RAX, and we see it's a pointer to the value, and we can examine it, and we see, yeah, it's the string Kamehameha, and we see that right here. Yeah, I believe what this value is I'm pretty sure this is a heap address, which you can see through the vmmap command. Yeah, this is a heap address, and I'm pretty sure this, I think, is the yeah, I think this is the wilderness value, but I believe this is just a piece of data related to the heap. So getting back to leaking, How is this going to work? It's going to be extremely simple. I'm just going to change this value size from OX0A to OX2A, so it should include a bit of the Piccolo record that follows it. Let's go ahead and run this again. And we see that we're back at the same spot with return value at RAX. However, when we actually look at RAX, we see that, well, first off, looking at here, we see that, oh, hey, there's some other data. Looks like it's this record right here. And when we go ahead and actually, well, how does this string start off? 6963.6F. Looks like around here is where it starts. So let's go ahead and take a look at it. Yeah, we see part of the record that we're actually able to leak with that. The reason why we're not seeing the full string is because I started examining it as a string halfway through the data, but we can clearly see here that we were able to leak subsequent data from the database when we're just querying a single record. And like that, by editing the database save file, we're able to query one record when in reality, we are actually leaking data from subsequent records. So another fun thing that we can do if we can write to the database save file is that we can alter a record such that when we update the record, we can actually overwrite subsequent records. For this demo, there are 3 files that I will run. First being database file creation. This is just responsible for effectively creating a new database and inserting 3 records into it. Second being database querying, which this is responsible for just querying the record Piccolo from the database. And the third being database insertion.c. This will update a record with a really long string, and this record is what will actually do the record overwrite. Now I will run database file creation. That created a new database save file, which I will copy over to the database save file that we will actually write over with the record and where the record overwrite will take place. So just go ahead and copy and paste it. Now for this database querying.c, it's querying for the Piccolo record. So when we go ahead and run it, we see that it returns the value that we expect. Now let's go ahead and take a look at this database save file in an actual hex editor. For this down here, we see the 3 records that we expect to. Also, similar to the database leaking demo, this demo is fairly similar, basically exact to the demo I have linked to my docs in the description below. But yeah, for this, I'm not going to go over to all the nitty-gritty details why, but basically how this attack works is we just expand the value size of the record such that when we go ahead and update it, it sees that, oh, hey, this record is, let's say, OX40 bytes big when it's only like OX08. So it will allow us to overwrite subsequent data. For this, I'm going to overwrite the size value with OX6E, which should go ahead and do that. Save the database file, and then we run database insertion, and then we try to query the Piccolo record. We see that we can no longer do that. And when we take a look at the database save file again, we see that all of those records have been overwritten. So just like that, by editing the database save file, we were able to leverage a database or a record update in order to actually overwrite subsequent records. Hello. So in conclusion, we covered some of the various inner workings of this database implementation and also showed some fun things that we can do if we can actually write to the database save file. That being said, one thing I'm sure many of you are thinking right now is what good will this be? If we can already write to the database save file, we can already overwrite and read the subsequent records. And to a certain extent, that is true. What I would say is the data that we're trying to either overwrite or leak might not exist in the database at that time, in which case something like this might potentially come in handy. Although one thing I will say, with the attack surface being literal database save files, it makes trying to use this pretty difficult.